Hey, Maddie. So this is really kind of two problems in one. And one thing to remember when we do these circuit equivalencies is really we are trying to get down to basically just one resistor in the whole shebang. So you simplify. So we're going to take this, right, and you can break that down into this R1 resistor, and then we can solve for the parallel and turn that into another resistor. All right, and if the problem warranted it, then we could take those two resistors and now turn that into one resistor. So that's kind of what they're getting at when they talk about this resistance equivalencies, is you can always simplify through these steps. So here's step one, here's step two, take the parallel and put them together, and then take these two in series and put those together. And you might have 4 or 5 as you do more and more of these. All right, so if we look at your case one of 560 ohms and case two of 1,000 ohms, okay? So the first thing we're going to do is we are going to simplify this and get this into what is the resistance across these parallel resistors. All right, so we know the equation is 1 over RT equals 1 over R1 plus 1 over R2 plus however many you got. But here we just got 2. All right, so if we plug in the case number 1, all right, so that's 1 over 560 plus 1 over 560, and then you got to take that, and a lot of students forget to then go 1 divided by RT. You got to take the inverse. So we then get RT for case number 1 as 280 ohms, and then for case number 2, 1 over 1,000 ohms plus 1 over 1,000 ohms, take the inverse, we get 500 ohms. Okay, so in case number 1, this, all right, when you simplify it to this, all right, it's 280 ohms and 500 ohms. Then we have the two of these, and this necessarily, it's not really germane to the problem. I think it will help you solve it or understand it better rather than solve it, because you don't necessarily really need this section. But basically what we're saying is, okay, now we've simplified it to this, all right, how do I make it into this? All right, so we have one resistance total. So in this case we have 2 resistors in series, all right, so those are just added together. Okay, so then we get the 560. All right, and we're doing case number 1, 560 ohms for this first resistor plus the 280 resistor, which is the 2 together. Okay, and that gives us 840 ohms. And then in the case number 2 with 1,000 ohms, we have 1,000 ohms up here, and then combined, because it's split, when we combine those we got 500, so we get 1,500 ohms total. All right, not really needed for the problem, but I think it will help you get your head wrapped around it, because then one of the questions you asked is, why is the current not changing? Well, it really is. Over the entire circuit, all right, over the entire circuit, the current is changing between these case 1 and case number 2. And if we plug in, all right, if we use the V equals I times R, all right, and the reason I draw this little shape is that I think it's handy for students to, if they draw this, then they just put their finger on what they're solving for. I'm solving for V, I'm solving for I, all right, in this case we're going to solve for I. Voltage divided by resistance is what I'm looking for. All right, so in number 1, if I plug in my numbers, 5 volts divided by 840, I get 5.9 microamps. And if I plug in second case, 5 volts divided by 1,500 ohms, 3.3 microamps. Now that's going to show up as 0.0033 something, right, on your calculator. But 1, 2, 3, move the decimal place 3 points, it's micro. Okay, it's a little easier to say 3.3 microamps than 0.0033 amps. All right, so then for your question, all right, what is the current? All right, because we want to solve this V out. What is the current after R1? So we're going to need that. We need, so as the electricity flows here, we are losing some of our current. as it flows through that resistor. All right, so if we cover up the I, so we want to do V divided by R. So I, for case number 1, 5 volts divided by 560, which is sort of our case, and we're just looking at the drop across this one resistor. All right, so that's 8.93 microamps. And then if we solve for case number 2, where we make this 1,000, 5 divided by 1,000 is 5 microamps. Okay, so then if we want to solve for V out, right, which is what is our voltage drop across these 2 points, right? So we've already consumed doing some work for this resistor that's dissipated in heat, all right? So then we want voltage is equal I times R, okay? We figured out what current is at this point, right? So the current's going in, so that's going to be your I, and that's what we solve for here and here for our 2 different cases. And then we'll plug in our resistance that we calculated using the parallel formula, so 280 and 500, okay? So the V out for case number 1, 8.93 microamps times 280 ohms, 2.5 volts. Same thing when we do number 2, we use completely different numbers, 5 microamps, which is from here, plus the 500 of the combined resistance across those 2 equals 2.5 volts. All right, so that's how you get the same voltage across those series resistors, or the parallel resistors. All right, hope that helps you. Bye.